The last sort of part is going to be, well, initially out of context, I suppose, but I'll try and put some context with it and we'll finish it off in tomorrow's lesson. But that's looking at how we can solve a 3x3 linear system. Importantly, yes, your calculator does it really well, but it only does it if you can put in the coefficients of the x, y, and z and the constant in as actual numbers, and it'll solve it. That's perfectly okay. What you're going to find, though, is a lot of the situations we're dealing with is that the coefficients will involve an unknown or multiple unknowns, and so you have to be able to do this method to be able to solve them. When we have a look at an example, I'll sort of show you why we would do it, but hopefully you can look at this sort of thing here and say, oh, that's very much like planes. Okay, the equations are planes, and so you could imagine this could represent, these three here, could represent three planes in space. Perhaps we can find something out about them. Okay, but for the minute, let's just think about this as a system of 3x3. There are multiple ways you can solve 3x3 equations where you've got the unknowns that you need to find. But this method, which is using the augmented matrix form, is a nice sort of straightforward follow the steps sort of method, and it'll get you to a point that you can solve it. The aim is to write a matrix that looks like this, where you just put in the coefficient of x, y, and z for the first equation that you've got, and then the answer or the constant term over this side, and then the x, y, z coefficients for the second one, and the constant term for the second one, etc. You write it out in that sort of form, putting that line down there to sort of separate out the coefficients to the constants. But you could imagine, rather than having it A1, B1, C1, etc., you could imagine that they were just given A, B, C, D, etc. letters. What we're going to try and do is manipulate it so that what we get is some numbers that are non-zero, perhaps non-zero in this space, but we have this little triangle of zeros that occur down here. The reason being is if we look at this last line now, that last line really would read that h lots of z is equal to I. Now, if h was, say, 3 and I was 4, then we would say 3z equals 4, and we would get a value for z. We could then, once we had a value for z, we could plug it into this line of equations, okay, because you'll have a y unknown, but you'll have a, whatever the f is, lots of z. Well, we know what z is now, so we can put that in and g will be a number. So you will be able to work out what y is. Once you know what z and y are, you can go to the top line and plug them in and solve that. So that's the steps, that's the process that we're aiming to do. So you can see I've just made it bigger there. What does that mean though? Okay, and so if we get, there are sort of three possible outcomes, and the h they're talking about is this spot here. So if that value there, okay, is not equal to 0, all right, then what we can say is that we can work out what the value of z must be. It must be a unique value, it must be a singular value, all right? And that means if that's unique, then once we've worked out what z is, we can plug it in and work out what y is and plug that in. Then once we know what y is, plug it in to get z. So in that first dot point, it's saying if the h value, if this is not 0, then there must be a unique solution, a unique set of x, y, z that solves that set of equations. Okay? But if h equals 0, so there's no reason why we couldn't have it come out as being A, B, C, D, 0, E, F, G, but the h comes out as 0 itself, so I would be a number. Now, if you think about that, that's saying that in this bottom line, that 0 lots of x plus 0 lots of y plus 0 lots of z is equal to I, a number. Okay, now if that number is not, if I doesn't equal 0, we can't solve that. There's no solution. There's no values that we can have for x, y, z because there's 0 lots of each to become up to a number. Okay, so that's what our second dot point here is talking about. If h is equal to 0 but I doesn't equal 0, there is no solution. There is no values x, y, z that will satisfy all of those. Potentially can happen. Okay, the last dot point is saying, all right, if we do get zeros here, but I is also equal to 0, then this bottom line would tell us that 0 lots of x plus 0 lots of y plus 0 lots of z is equal to 0. Well, it doesn't matter what x, y, z you put in there, it's always true. It's true all the time. So what that tells us is there must be an infinite number of solutions that will work for that series of equations. And we go one step further and we say, okay, well, we don't know what z is going to be equal because z could be equal to anything. Let's assign z to usually a t as the parameter. So once we know that z equals t, we can substitute that back in and work out what y is. It'll be in terms of t, and what what x is in terms of t. So there's 3 possible outcomes. All right. They're going to perhaps make more sense as we go through. So the first set of example, or the first example, is to look at the set of equations there, which are labelled A. So consider that's 3 planes. Okay, now the reason why I say it's 3 planes is to help put some context to it. Before we actually do the work, you can see down here at the bottom that it tells us that we do have a unique set of solutions in this one, where x is equal to 2, y is equal to 4, and z is equal to -1. What that tells us is those 3 planes must meet at a singular point where x is equal to 2, the coordinates 2, 4, -1. That is the only set of coordinates that will work for all 3 planes. That's effectively what's happening. Now, we wouldn't know that until we'd done the work, so let's have a look at how they actually go about it. In your setting out, I don't necessarily expect that you do the stuff on the right-hand side there. Okay, that's sort of the working. But let's have a look. I'll just make it a bit smaller and see. So, here's our set of 3 equations. The coefficients are going to be 1, 3, -1, and then the constant is 15. So 1, 3, -1, 15. 2, 1, 1, 7. 2, 1, 1, 7. Okay, so that's how he set it up. So the first line, this is directly just copied basically across there, just the coefficients and the constants. Then we want to go through some processes of changing. Our aim is to get these zeros here. But usually our first step is to get a 0 in this spot and a 0 in this spot. And all we are doing is the elimination method that you might have been taught before with simultaneous equations. You don't have to think of it as that, but that's what we're doing. We call them row operations. What we can do to our rows, so our rows going across, is we can change them as long as we multiply them by constant values. So we could double each value. Okay, we could halve each value. We do that. The other thing we can do is we can add or subtract one row from another row, and that's acceptable. Okay, because this is a system of equations, so that can be done. So what we would normally do, and they've written it, this row here has obviously changed. It was from this one. Okay, and what they've done is they've said, I want to get 0 in this space. And so they've used, and we would usually do it in our first step, we would usually do, right, what can I do from this row? What can I use this value, okay, to be able to make it so that this value plus this value is equal to 0. Now, because they're both positive, we say plus doesn't work, so we would take. So if I said, hang on, if I wanted to get 2 down to 0, I need to take 2 from it. Well, I've got 1 here, so if I double this whole row, what I would get, I'm going to write it, well, actually it's written here for us, but if I double this row, I get 2, 6, negative 2, 30. Okay, that's just doubling that row. And I'll just underneath, just so you can see it, I'll just write 1, 1, 7. So that's row 2. That's, and in fact, just to make it so that you can see what's happening, I will, actually no, I won't, I'll just write 1 minus 1 minus 2, 0. So that is still the same set of equations. Okay, it's just doubling the top line. It doesn't matter that you double everything on it. But from that point, if I said I'm going to do row 2, the second one down, take row 1, okay, what I'm going to get, and I'll just write it underneath, this is not very good setting out, but just to show you what's happening, 2, take the 2, okay, is 0. 1, take 6, is minus 5. 1, take negative 2 becomes 1 add 2, which is 3. And 7 take 30 is negative 23. Okay, hopefully you can see that's what this row here actually is. Okay, so what they've said and what they've written is that this line here means row 2, so this row, row 2 is this row here. Row 2, take 2 lots of row 1, so 2 lots of this row, becomes the new row 2. Okay, so that's like the step. They've shown like working out here. They've written, okay, there's row 2, and they have taken 2 lots of row 1. They've actually put the take in the spots there, and then they've solved it and put it into that. Oh. Right. I don't know why that mirroring's disconnected for people in the room. Just bear with the pause in a video because I'm trying to reconnect so people can see it. Something's happened to the network. All right, I'm just going to stop that video now.